For those of us who develop software, a great source of data is the version control system. There we can find information regarding who changed the file, when they changed it, why they changed it, and what changes were made. In this unit, we'll see how to fetch data from a remote repository, how to say what changes were made through the log entries, how to annotate a file to see who changed what, and also how to fetch and examine old revisions. Let's start by fetching a complete Git repository, that of the Linux kernel. To create a local copy of a repository, we use the git clone command, followed by the URL of the remote repository we are interested in. In our case, I create a clone of the Torvalds Linux repository. After changing to the repository's directory, we can run various git commands. For instance, we can use git log to list the repository's commits. Git allows us to see a repository's commit, atomic changes recorded in the repository, in any format we specify. In the previous example, we introduced the git log command and listed the commits of the Linux repository. Taking it a step further, we now use the pretty equals format option of git log to display the name of the author of each commit. I remove Linus Torvalds using another interesting command, grep. Grep stands for Global Regular Expression Print. It searches in files or in the standard input for lines that match a regular expression and prints them. We'll study this command in more detail in the following units. The -v option of grep that I use here stands for invert match. It selects and prints non-matching lines. In this way, I exclude from the output the lines with Torvalds and print the names of the first 10 other commit authors. As another example, let's see who has performed the most commits. In order to find which author has made the most commits, I run again git log, but specify as the output format the email of the author of each commit as a unique identifier. Next, I sort all emails. I pipe the output to unique -c to count the occurrences of each author. These correspond to the number of commits an author has made. Then, I sort in reverse numerical order the frequencies of all authors, and I list the first 10 authors in number of commits. As expected, Linus Torvalds is in the first place. In the following places, we see other authors who have committed significant changes to the Linux kernel. To run git log on many files, we can use the find command to locate those files. As an example, let us see which file has the greatest number of changes. I first find in the Linux kernel directory all entries of type file using the find command. Next, I read all path names in a while loop. For each file, I echo its path on a single line. I don't specify a new line after the name because I want to append the number of changes. To calculate the changes, I run git log using the one-line format. I then pipe the output to wc to count the lines. Thus, the number of lines returned by git log corresponds to the number of changes. Executing the command, we get the name of each file followed by the number of its changes. Our goal is to find the file with the most changes. To do that, I repeat the above command sequence and then sort by the second field of the output, the numbers, in reverse numerical order. We notice that most changes, about 800, have been applied to the trace.c and cgroup.c files. Another spiffy git command is git blame. This allows us to list the file's contents together with data regarding the last change made in each file's line, who changed it, when, and through which commit. Let's see an example. I run git blame on the file kernel /fork.c and get lines 20 to 40 using sed. Sed is another interesting command that we'll examine in more detail later on. It stands for stream editor and performs edit-like operations on files such as search, find and replace, insertion or deletion. Here, I specify the N option to suppress automatic printing and ask it to print a specified range. Each line we get contains the SHA hash of the commit that lastly changed it. We also see the authors who made each commit, the date and time they made it, and the contents of the file. To process the output of Git blame with Unix tools, the so-called porcelain format is the most appropriate. Let's see an example of how to use it. Specifying the line porcelain format to Git blame, we get for each line the SHA hash of the last commit, together with the number of the affected line of the original file and the new file. We also see various key value pairs, such as the author's email, and the time the author made the commit. There is similar information for the committer, the commit's summary line, and the line's contents. Let's now see who has contributed the most lines in the file fork.c. Using again the line porcelain format, we can easily find out which author has contributed the most lines to a file. I run git blame with the line porcelain format on the kernel fork.c file to fetch all line metadata. I then pipe the output to grep to filter the metadata lines that begin with the word author. These correspond to the authors of the file's lines. In this way, we can sort the lines alphabetically by the name of the author. Next, I pipe the output to unique-c to count the author's occurrences. Lastly, I sort the authors in reverse numerical order to get those with the most contributed lines. I use head to get the first 10 authors with the most lines. As expected, the first is Linus Torvalds with almost 600 changed lines, followed by Oleg Nesterov with about 200 lines. As a final git blame example, let us find the average age of the lines in one specific file, an aggregate measure of the file's age. In order to calculate the average date of a file's lines, we can use the date expressed in seconds, which can be easily aggregated and averaged. As you may remember, running date with the %s format displays the time passed since the epoch, January 1st, 1970, in seconds. This is how we usually express time on Unix. We can also do the reverse. Using the -d option of date, we can convert seconds since the epoch to a date. We precede the seconds with the @ sign. As another example, I specify 0 seconds and we get as output the beginning of date and time of the epoch adjusted to my current local time zone. Back now to our initial goal of finding the average date of all lines in a file. I repeat the date command with the -d option. The number of seconds is passed as input from the command sequence. In this sequence, I first use git blame with the line porcelain format for the file I'm interested in, kernel fork.c, in order to get the line metadata. The output of git blame is then piped to the awk command. Awk is a scripting language used for manipulating data and generating reports. It was named after the initials of its authors, Alfred Aho, Peter Weinberger, and Brian Kernighan. We'll examine the awk command in more detail in a later unit. In this example, I match with awk all metadata lines that begin with author time. For each of the matched lines, I add the number of seconds, which is the second field, to the sum variable. At the same time, I use the count variable, which I increase by 1 for each matched line in order to count the total lines. Finally, I print the sum divided by count, which is the mean authorship time, in other words, the average date of the lines. According to the result, this is August 20th, 2013. The git show command allows us, between many other things, to see a file as it was in any point of the past. Let's see, as an example, how we can track the evolution of a file's size. To track the evolution of a file's size, I first store the name of the file we will examine in a variable named file. Let's now process the file's commits. I run git log, specifying as the output format %h which refers to the SHA hash of each commit. As a result, we get the unique identifiers corresponding to every commit made to the particular file. Extending the git log command, I pipe the output to a while loop. In this loop, I read each SHA and then run git show on the SHA, followed by the file name obtained from the file variable. Next, I pipe the output to wc-l to count the number of lines. At the end, I pipe the output of the while loop to head to display the first 15 entries. The entries indicate how the number of lines changes as the file evolves. We notice over time they kept increasing from 886 to 988. This concludes our unit on fetching data from version control systems. Stay with us.